Start recording. Big S is entropy, and so we have the Boltzmann constant times the natural logarithm of the number of microstates. Well, this is a perfectly crystalline material. Everything's in a nice ordered spot, and it has no thermal energy to distribute between any of them. None of these little guys are vibrating. Okay? That we have one possible state that fixed in place like it is. That's one microstate. Remember, this is microstates. And then this is our entropy. All right, and so if W is 1, if we take the natural logarithm of 1 is equal to 0. All right, so we have a base point for what 0 entropy looks like, which is very useful because everything scales up from there. And what we can say, we can give ourselves a rule here, or take a rule from that, is as temperature increases, entropy increases. All right, and that makes sense. If we have only one microstate here, if we have no energy to distribute, suddenly if we increase the temperature a little, we suddenly give these guys some energy. They vibrate a little bit, but they don't all vibrate the same amount. We have distribution of energies in each of these. And so that energy can be, this one can have more energy than that one, has less energy than that one, has a whole bunch of energy for what the temperature is. And as the temperature goes up, we have more energy to distribute in different ways. Does that make sense? So that's why we think about how much since they're just spheres, think about them just as vibrating. And it's more there are more ways to distribute that around. So our entropy increases. Does that make sense? Okay. And we'll talk more about that in terms of entropy increasing as energy increases. So another thing I want to remind you of is we've talked, I think in this I don't remember if it was this semester or previous semester, but we talked about state functions. Okay, a state function is something that depends on, it's a property that depends only on the start and end state, start and end state. All right, so for example, where your dorm room is, assuming you live in a dorm room, where your dorm room is, let's say where your bedroom is located, the GPS coordinates of where your bedroom is located. All right, that is doesn't matter how you get there, doesn't matter whether you walk around Commons like 4 times and then go there, right? Or if you go straight there, all right? Regardless, it's in the same space, same place, right? That's a state function. All right, entropy is also a state function. Entropy, and we could say change of entropy for a reaction. All right, and that is really useful because what it means is if all I care about is the beginning state and the end state, is that if I want to calculate the change in entropy for a reaction, I can do it in different ways. I don't have to do it in a specific path. All right? And I want to remind you that we had this standard enthalpies of reaction we talked about. So what is a standard, and we used the standard enthalpies of reaction, we use standard enthalpies of formation to calculate things. So standard entropies of formation. We saw this concept before, but it was enthalpies. right? I'm going to try and keep my enthalpies and my entropies straight through this lecture. But enthalpy is heat, entropy is probability or disorder. You can think about it as disorder. Okay. And so what these are the entropies to make a compound at a given temperature from its elements. Entropies. The entropy I was thinking, is there ever going to be a decrease here? I think it's always going to be increase. I'm going to say increase. To make a compound, it'll be increase, it'll be 0. Compound from its elements. All right. So in other words, if we're looking at this table below, which is going to give this to us, let's take something we're not going to do. Let's take this methanol here. Okay, this is methanol. It's the stuff, if you're brewing whiskey, or if you're distilling whiskey, it's the stuff you want to throw away at the very beginning, okay, because it'll make you blind. Let me go ahead and make it outline in the color so we can see, so you're not feeling blind at the moment. And so we're going to go CH3OH, right? If I'm going to make one of these, that's a liquid, is it? All right, I'm going to make it from its elements. So I'm going to need a carbon, which is going to be a solid. Okay, I'm going to need 4 hydrogens, which is a gas. Okay, and I'm going to need 1/2 oxygen, right, which is a gas. So this value right here, this value right there, is the entropy change when this reaction occurs. Yes?
It doesn't actually be made like that, though, right? Like, it's not like you're taking, hydrogen from the air and oxygen from the air and combining it with, like, some solid carbon, right?
It's you don't do the reaction like that,
Okay.
or you can calculate these. So I can calculate what this reaction is, right?
Mm-hmm.
So and I actually don't know, and I probably should have read more carefully in your book, whether this is actually all from absolute zero. I'm guessing all of these are from absolute zero. So this would be at absolute zero, okay, at which point oxygen really isn't a gas. I don't know if it's supercritical fluid or what it is, but there's this or I should say a Bose condensate, but you don't want to know about that. It's another phase of matter that happens only Bose. But I don't know about that, but it's from the elements. That's all we need to know here. Okay? Is it in the book?
I think it says it 298.
Well, this is the make that, and then this is at 298. Right?
Okay.
But since we're doing entropies, let's look at oxygen. So the standard entropy to make oxygen, I'm assuming at absolute zero, is going to be 0 because you make it from its element, which is itself. Does that make sense?
Yeah.
So I'm assuming that all of these things are at absolute zero and their phases may change for that. Okay, but that's why we have an entropy associated with oxygen, because we're at 298 now.
Okay.
And it's more than 0. All right. Hopefully it wasn't confusing. All right. Ignore the discussion about absolute zero or not absolute zero from their elements, right? So that means you can have a table here of things. What does it cost to make these things? And then we can use that to calculate the entropy change for other reactions. And that's where this is useful. So what I can do is if I have a reaction, and let's say this is my reaction. All right, this is one of those lovely times in chemistry where it's always products minus reactants, okay, which is most of the time. So what I can do is I can take the enthalpies of formation I'm sorry, the entropies of formation here, if I'm trying to find the change in entropy for this reaction, I can take the entropies of formation of the products and subtract the entropies of formation of the reactants from them. All right, and your book presents this as a general equation, which I'm going to give you, what I'm going to write right here, but I'm going to admit to you that whenever I've taken classes and I see these things, it's a very mathy thing, and I always find it confusing. So I'm showing it to you because it's in your book. I'm also showing it to you because, you know, the more times you look at this sort of stuff, the less confusing it hopefully is. All right, so if we want to do this as a general equation, the standard entropy change, so the little dot circle means standard, the standard entropy change for a given reaction, could be the reaction above, is going to be equal to, this is where I always get confused, somebody puts a something in, right? And then they'll maybe put an I in, I'm not going to put the I in, but they'll do an I into a, you may have seen this, the sum of all of the entropies of formation of the reactants, products, minus the sum of all the entropies of formation of the reactants. So with this little summation thing, what that just means for our reaction up above is that the entropy change for this reaction is going to be equal to the entropy change of formation of this, right? Oh, I forgot part of this. Just to make it more confusing, I'm going to put an N in front. It's how many moles there are. So it's the entropy, the standard entropy of formation of this, plus the standard entropy of formation of this, times 2, because there's 2 of them, minus the standard entropy of formation of this, minus the standard entropy of formation of this, times 2, because there's 2 of them. Okay? Let's go ahead and do that.
What does the RXN stand for?
Reaction. Good question. Yes, Priscilla.
CH4, is that an S or a G? Is it solid?
Where are we?
In the state?
In this?
No, the
CH4. CH4. That's
Yeah.
CH4 gas. Okay, so let me go ahead and move this up just a little bit so we can see all of them. And so we could calculate this for this reaction up above. We're looking at this reaction we're calculating it for. So what we're saying is that the delta, the standard entropy of reaction for the reaction up above is going to be equal to the standard entropy of formation of CO2, right? Plus 2 times the standard entropy of formation change. I moved my circle there. Of formation of, so here was where we are now, of water, right? And there were 2 of them. Minus, because now we're going over to the reactants, the standard entropy of formation of methane, plus, because it's a minus plus, is going to be the standard entropy of formation of oxygen. And I forgot to put the times 2. There are 2 oxygens, right? So 2 times that. Okay, now we can just put in the numbers. We'll look the numbers up on the table and put them in. Before I do that, any questions of what I'm doing? Products minus reactants, yes.
With the change in S, is there a circle, like, up top? Like, change S?
This thing,
Yeah,
that means standard conditions.
I just need to. Thank you.
It's standard conditions, and this temperature here is standard conditions. Okay, so now we just look things up on the table and go with it. So I've got the standard entropy of formation of oxygen at this temperature is 205.2 joules. The standard entropy of formation of water at this temperature, and it was a gas up here, right? So we'll do the gas one, is 188.8 joules. Okay, and these are really per mole, right? Per mole of reaction. Whoops. This is going to then minus the standard entropy of formation of methane. Where was that? Gas. That's right here. So 186 point, is that a 3? Joules plus 2 times for oxygen, 205.2 joules. Yes, did I miss something?
Yeah, it should be I think for O2, it should be, wait, I think
It's
it's
Oh, by
CO2.
CO2, I
It's
put down the
CO2.
O2. Thank you. That's a 213, right? Thank you. So this one should be here. Whoops. That's this. So 213.8, right? Okay, thank you. All right, so now we can just put those into our calculator. And I recommend you do this just for the practice of using your calculator for multiplying and divide. You know, if you're using parentheses, whatever it is, you're less likely to make a mistake if you practiced it more. I used it earlier for a previous class for a validation that my calculator actually does order of operations correctly, even though I know it pretty much does. I got negative 5.38 joules, okay, for this reaction. And that's assuming these are all per mole, so that's assuming we have 1 mole of this, 2 moles of that, etc. Okay. Does that mean over the reaction entropy increases or decreases? It decreases, okay? So things become more ordered, you would think about, if you like to think about entropy as order, as this reaction occurs. And it's not a very big change, and I don't have a good, we'll talk about different ways you can think about this, but I don't have a good explanation for that. I could make some things up, but questions? All right, I would like you to do the same thing for this top reaction here. You can't see it?
Yeah.
Thank you. All right, so let's make it nice and big. Can you see the table above? Yeah or no? Can everybody see the table? Caroline, do you see the table above? A little bigger? Sure. All right, Dakota, that's one of your jobs. Tell me when things are too small. Whoops. You can also tell me when they're not on the screen. What? Uh-oh. There we go. Okay. I feel better. All right, so we're just going to do not the blank space, but we're just going to do this one because that's what we have the data for above. If you have questions, call me over. So 30 more seconds. Okay, let's go ahead and work this one. I'll go ahead and work this one. You've been working it. So we're going to do products minus reactants, right? So my standard change in enthalpy for the reaction, did I say enthalpy, entropy, for the reaction is going to be equal to the products. So I've got two waters, right? So the standard change in entropy for a formation for water minus, then we've got the hydrogen, right? 2 times the standard entropy of formation of hydrogen gas plus the standard entropy of formation of oxygen gas. We'll just remember, I haven't been writing the phases down. We'll just make sure we get them right. Okay? Questions so far? And then we just put the numbers in. And what I get is I'm going to have 2 times 188.8, right? That's going to be joules per, I was just saying joules before, but it's per mole times Kelvin, right? Minus 2 times, where's that hydrogen gas? There it is. 2 times 130.7 joules per mole Kelvin plus, where's the oxygen? 205.2 joules per mole Kelvin. Questions so far? I'm going to go ahead and put it in my calculator. I don't remember what the answer was last hour, but 2 times 1. Okay, now I remember. I saw this one before. So, did you guys get 89? Okay, so that's equal to 89 negative. Thank you. That's important. Joules per mole Kelvin. Right? So does entropy go down or up or down here? Down. Okay. You have a question?
Yeah, I was gonna ask, technically at 298 Kelvin though, would it be, like, even if it's the two gases coming together, wouldn't it form a liquid?
We're not going to worry about that. That's what they're saying for that or before it condenses. We're going to have to, we've been given a reaction, and that's the way we're going to calculate it based on the things we have. Okay. So we assume that it's a gas for a while. After the reaction, these molecules have the energy from, I mean, this is a really violent reaction, actually. It's what it's part of the reaction that sent the space shuttle into orbit. And so they were making all the water gas come out of that. I agree, though. Okay, so we've got this. Okay, so what I want to do is take a look at this real quick, though. I would have predicted ahead of time that, yes, entropy would decrease. And the reason I would do that is when I look at this reaction, I've got 3 molecules, right, to make 2 molecules. You think about distributing heat or energy around, there are more ways to distribute it in 3 molecules than 2 molecules. Does that make sense? So whenever you have a reaction, if it makes fewer molecules, we're going to have other things that influence entropy as well, but if it makes fewer molecules, we expect entropy to decrease. If it makes more molecules or more ways to distribute it, we expect entropy to increase. How about this reaction? Entropy is going to decrease or increase? Increase, right? Because we start with 1 and we go to 2. More ways to distribute the energy in those 2. Questions? Okay. So in addition, so I'm going to actually write that out though. And all of these rules are all other things being equal, right? Because if the temperature decreases and I make more molecules, now I've got two things that are conflicting with each other. I'm not going to give you that unless it's in the form that you have an equation to solve it. Does that make sense? There's an equation of doing that. So if more molecules are made in a reaction, the entropy increases. All right, down below we see another example. Here we're mixing gases. All right, this is similar to if you had a glass of water and you drop a dye into it. What would happen to that dye if you let it sit for a day? It would distribute everywhere, right? The dye would evenly mix throughout whatever container you had there, assuming it's water, right? You've got a liquid that it's going to go through. So if mixing occurs, entropy increases. All right, so you would, hopefully this makes sense. If I had two different gases here and I opened up the stopper here, I opened it, took the stopper out, so now these could mix, they would mix to where both gases were evenly distributed across both chambers. Okay. Intuitive? Hopefully based on your experience. All right, final one we're going to do here is if there's a phase change. Okay, if you move to a more mobile phase, entropy increases. All right, so what I'm talking about here is as you go from a solid to a liquid, those molecules become more mobile. As you go from a liquid to a gas, those molecules become more mobile. What's going on is you have a greater range of motion energy that those molecules can have, right? Here they can't really move around, they can just vibrate in place. So there's only a small range of energies each of those can have and still vibrate in place. Here, now they can roll over each other, but they're still touching. So we have a larger range of energy they can have. And then finally, when we get to the gas, they're bouncing all around. We have the largest range of energies that each of those particles can have. We have the largest different possibilities. Yes?
Is that true? Any like increasing kinetic energy, so like adding or increasing the temperature of any substance, the entropy is going to increase because it has more motion?
Yes. So increasing the temperature will increase the entropy. Okay. And so all of these rules I'm giving you are all independent of each other. So I'm not going to give you something where two of them are pointing at each other. Does that make sense? Okay. I may give you something where you have an equation that you can use to solve for the entropy change. We'll get to that.
Isn't that the whole point of like the Gibbs free energy equation though? Like you determine whether or not like.
We are going to get to the Gibbs free energy equation. Hold off on that. Okay, we're not going to get to it today. So ask me afterwards. All right, so and this is an example of this. This looks kind of like our heating curves, except that our straight lines are vertical instead of horizontal. Remember our heating curves? And so when we've got a solid, when it gets to its melting point, here we're talking about the entropy increase with temperature. The entropy is going to change while the temperature doesn't. Remember, we hold still. As we add heat, the entropy goes up. Same sort of thing here. This is for water. As we add heat, the entropy increases. And that comes from our Clausius definition of entropy. Remember was it Rudolf Clausius? What he said was that our change in entropy is going to be equal to the heat that we add or subtract over the temperature. In regards to these changes, we could say that the entropy of fusions, that's the melting one, is equal to the enthalpy. Remember we had an enthalpy of fusion over temperature. And if you remember, this was in per mole, right? This was molar. So when we go back to that, I don't know if I cursed in this class. I remember looking at it going, why on earth are enthalpies of fusion in moles and our heat capacities are in grams? That's so confusing, right? This may be why, actually. I hadn't thought about it before. This may be why, because here your definition of entropy is based on a molar heat of fusion. And then our enthalpies, or entropy of vaporization, alike will be equal to our enthalpy of vaporization over our temperature. And so, just once again, this is molar, not per gram, per mole. And then this is in Kelvin, as is going to be the case for most of our stuff here. Questions? Okay, so now we've got some new equations to play with. We have some old equations to play with, but a new context to play with them. Let's go ahead and try a problem. All right, so this one's about enthalpy of fusion, right? So I can scoot it up just a little bit, but it's the same as the enthalpy of vaporization problem. Go ahead and see if you can solve for temperature there.
That's right. I was asking, like, you said that you wanted to do this things, but isn't that the only one using the equation? Like, if you're determining this quantity of something, and then you have conflicting, like, there's gonna.
Right, you got it in terms of the heat versus,
Yeah.
but that's, we're going to that equation to talk about.
Okay.
And really, we got an entropy term, separate.
Oh, that's fair. Because you have to convert joules to kilojoules. Do you divide by 1,000? Oh.
Okay, let's go ahead and look at this. So our base equation is our change in entropy. This is for, we're doing fusion, right? For fusion is going to be equal to the heat of fusion over the temperature. We're solving for temperature here, right? I'm going to go ahead and instead of putting the numbers in first, I'm going to solve the equation and then put the numbers in, just to do it a different way. So I'm going to multiply both sides times t, because that's what I want to solve for. I want to get out of the bottom. That's going to give me the temperature change. That's going to give me this, right? And then I'm going to divide both sides by my enthalpy, or my entropy of fusion. Okay, and then that gives me right? Okay, and now I can just put those numbers in and solve. So on the top, actually that's in kilojoules. I'm going to want to get my units the same, right? I'm going to be divided by kilojoules and my entropy is in joules. So I need to change those. How many joules in a kilojoule? 1,000, right. And so does my 1,000 go on the bottom or the top here? Top. Because 1,000 joules is equal to 1 kilojoule. I need to put the kilojoule on the bottom so that these will cancel. And I'll end up with 37,700 joules per mole. All right. And so then for the temperature calculation here, on the top goes 37,700 joules per mole. On the bottom for the entropy goes these, 32.1 joules per mole Kelvin. All right, I'm happy to see that my units are all going to cancel nicely. So I've got this cancels with this, leaving me with a 1 over Kelvin on the bottom. 1 over something on the bottom is the same as it being on the top. And we end up with 37,700 divided by 32.1, and I got a temperature of 1170. That's what I'll do for my temperature. Kelvin. What's that in Celsius? 897. So we subtract to put that in 273 to put that in Celsius, right? And is that hot? Yeah, it's really hot, right? Does that make sense in the context of our problem? What's melting? It's a metal with a non-metal. What do we call that? It's a salt, right? It's an ionic compound. By the way, I did this with the other class. I'll do it with you guys too. So it makes sense that it has a high temperature, right? Salt melts at a really high temperature. This is an example of a salt. Table salt melts at a high temperature. To write the formula for that. You should be able to do that. You might need a quick glance at the periodic table, but your glance at the periodic table shouldn't be for zircon. Yes.
Would zirconium, zirconium fluoride or like any salt with a group, like the middle of the periodic table metal, would those have a higher or lower melting or boiling point than a group 1 or 2 salt?
We had trends for that. It's based on the charge. The melting point is going to be, so I got a question here about what's the melting point of a salt going to be based on? It's based on the charge, right? The higher the charge, what happens to the melting point? The higher the melting point, okay? And the smaller the smaller it is, the higher the melting point. So the greater the charge, the more attraction. The smaller they are, the closer they are together. That comes out of Coulomb's law, which I'm not going to remember. Coulomb's law, this is not part, is going to be remembered as the force. We've got the charge of one and the charge of the other over, is it just R or is it R squared? I can't remember. It's R squared, and then we have some constant down here. What letter does that get? Okay, thanks. Okay, so it comes out of Coulomb's law. The greater the charge is, the greater the force of attraction, the higher the melting point, and then the closer they are, the smaller this is, the greater the force.
Well, I was going to ask in terms of like unmelted, especially because metals like with the periodic table, there's like a lot of overlap of electrons and stuff because of the electricity model and all of that. So would that act as being like a greater R? Or like does that impact the strength of the attraction between
Right. I'm going to answer that real quick, but you talked about the electron C model. That's not, we don't have an electron C here because we're a salt, right? If it was zirconium metal, what it would be, then you could have a C in that electrons. But once dissolved, that breaks up. It's not a compound. It's not a compound, but it's not a compound. So why do you not look here though? Why do you not look here for what the charge is on? It's a transition metal. These have all sorts of charges, right? You might have some of them memorized. And some of them are actually fixed. Zinc is always +2. Silver is always +1. Okay? But a lot of them are not. Iron can be +2 or +3. Copper can be +1 or +2. I don't know what all the states are for cobalt, but I know it has a +3. So there are various things. You can reason them out based on filling shells and not half filling shells, but it's better. There's enough exceptions that it tends to be a memorization exercise as well. And so whenever you're given the name of a compound that's in the transition metals, they're going to tell you what the charge is right there. All right, so you should have looked at the name. You should either remember that fluorine was -1 or looked up and seen that on the periodic table. And this would be ZrF3. Okay? Still should be able to do that sort of thing. All right, so we had a high temperature. It's a salt. That doesn't surprise us. Let's go ahead. What's that for time? Yeah, let's go ahead and try this one as well. So here's another one where we're going to use those same equations. And I'll just go ahead and remind you that our entropy, what is this, fusion? We're doing fusion again, but it would be the same for vaporization in terms of our equation. It's going to be equal to our enthalpy of fusion over the temperature. We're just using the Clausius definition of what entropy is here. I'll give you 2 minutes, let's say. Call me over if you're stuck or you have questions. Okay, was that 2 minutes? Okay, go ahead.
Oh, I just had a little safety question.
Yes, you would. No, you take the smallest, so this is all multiplication and division, so you just take the smallest things. If we're subtracting, so what we could convert this to Kelvin, right? It started out with 4 sigmas, yeah. So I would go, yeah.
Actually, we're using a lot of it.
Well, we are, but we only know this to 2 sigmas. So we're losing 6 things on one, but it's because of if you're really sloppy about part of it. So when I make a solution of that, if I weigh out something to 4 or 5 significant figures, could be possible, and then I take a graduated cylinder and I slop it to the beaker, I'll better plus 5%, plus or minus 5%, to 2 significants. That makes sense. Regardless of how carefully I weighed it out, if I make my volume to plus or minus 10%.
So you really need to.
Yeah. So for biochemistry, which is more like cooking than baking, they're not my makeup solutions. I would only ever have two sig figs on because I'm not making a bit more careful behind the scenes.
Okay, thank you.
Okay, let's go ahead and take a look at this. So what we've got is we've got this equation here. Here is our, whoops, that goes here, right? And then here is our temperature, which goes there, except that I have to convert it to Kelvin, right? So I'm going to add 273.15 if I want to that, right? But I'm going to just do the 273 because I only have two sig figs elsewhere, plus 156.6. So convert to Kelvin. So that would be my 156.6 plus 273 equals 429.6, right? I think the earlier class I made a mistake where I subtracted instead. What would be wrong if I subtract, not for this one, but for a different one, previous one? How would I know that it was wrong if I subtracted this from that?
Oh.
I'd add up a negative what? Kelvin, right? There's no such thing as negative Kelvin, okay? There's no even special in a black hole version of you can have negative Kelvin. I've never seen it, okay? No such thing. All right, so then what we're going to have here is, this time I will not pre-solve the equation. So we're going to have 429.6. We're solving for our enthalpy of fusion, right? So that's going to be this, 0.021 joules per mole Kelvin. All right, this is Kelvin. I've got Kelvin on the bottom on the left and Kelvin on the right, so I'm going to go ahead on the bottom on the right so I can cancel those Kelvins. And so then I've got 429.6 times 0.021, and I get 9. 9.0 joules per mole is equal to my heat of fusion. Questions? Really low. Okay. Easy to melt that stuff. Questions? Okay. Then we're going to end up here. I'm going to give you, so these are 4 questions. They are not mathy. They are, can you apply the rules we've talked about above? Okay, one, you need to think about an equation. But can you apply the rules above and decide whether entropy goes up or goes down for each of these changes? And I'll go ahead and give you 2 minutes, unless you need more. Call me over if you're not sure, you want to talk about something. Okay, so let's go ahead and look at this. What about the first one? The first one's actually kind of the toughest. Entropy increases or decreases? What was that? It increased because we're adding heat, right? Is one way to think about it. We're adding energy. The other way to think about it is that my entropy change is equal to my temperature times what my heat is, right? I'm adding positive heat, all right? And my temperature is in Kelvin, so my temperature is going to be positive or negative? Positive, could be 0, right? But if I add some heat, it's not going to be 0 anymore anyway. So, so this is going to go up. Okay. What about the next one? We've got water gas going to water liquid. Entropy decreases, right? There's less of an energy range for those particles, so there are less possibilities. How about the next one? Decrease, okay? We've got something that's in water, can bounce around in water. We've got something else that's in water, bounce around in water. And we go to something that's a solid, it's precipitated out, it now can't bounce around, it doesn't have as much motion. And then we have something that is still dissolved in water. So that's gonna, we said decrease. How about the last one? Increase, why? Yep, increased number of molecules, so there are more ways. I've got 1 molecule here and 2 molecules here. There are more ways to spread the energy out here, more different possibilities. So that's going to increase. Questions? Questions on anything from the lecture? All right, well, it pains me to do so. I'm going to let you guys out early again. Come up and if you have other questions.